that. We're thrilled to have Susan Mazur here today. She is the field director of the California Phrenology Project and professor of ecology and evolution at the University of California, Santa Barbara. Thank you for being here.
Thanks. Being last gave me plenty of time to think of more shit to say. Thank you for that. But it also has made my mouth really, really dry. Thanks to you for that too. So studies of plant phenology are useful for tracking the effects of climate change on plants because phenology can change really, really fast. As a result, phenological studies tell us something about how different species perceive environmental variation in time and in space, and then how they reflect that experience in the timing of their flowering, leaf out, fruiting, etc. On the other hand, we know very little about the effects of phenological change on plant performance and persistence, and you'll maybe be happy to know that this talk will do little to change that. So for example, it's not necessarily adaptive to change phenological schedules in response to, say, a warming winter. If a species loses its pollinator, for example, then climatic effects on seedling survivorship are perhaps quite moot, or at least secondary. Okay, so today I'm going to tell you a little bit about the California Phrenology Project. I'll call it the CPP, thereby shaving about 15 seconds from this talk. The CPP is a statewide phenological monitoring program set up to track the effects of local climate and climate change on the seasonal cycles of wild plant species. We were funded by the National Park Service Climate Change Response Program, and so all the initial work began in 7 pilot national parks. Our scientific goals were to establish a phenological monitoring network, which has since extended into several UC reserves, botanic gardens, outdoor education programs like Nature Bridge, using standardized protocols established by the National Phenology Network based in Tucson. We wanted to cover a large geographic area, sample across environmental gradients, and ultimately begin to assess the effects of climatic conditions in time and over space on the seasonal cycles of California taxa, with the ultimate goal of beginning to predict responses to future climate change. And so we're only a few steps, a short way along these steps. Because we were funded by the Park Service, we had some public aims as well. We hoped we would come up with some plans to begin to be able to guide some resource management decisions that might be positively informed by some phenological information. We're not there yet. We needed to educate park visitors. We've done a lot of that. Through a series of many workshops that I implemented with my postdoc, Liz Matthews, who did such a great job. She's now permanently hired by the National Park Service in DC. We prepared many members of the public to observe and to interpret changes in our landscape. And we've succeeded to some degree in engaging citizen scientists in genuine research. We've got a website, go check it out, paying special attention to these tabs that introduce you to the species, the parks, where they're monitored, and we've got some educational tools that you might find useful in the classroom or outdoor education context. So just some stats in a nutshell. We targeted 30 species for monitoring in our 7 pilot parks, 8 of which are monitored in multiple parks. We tagged, mapped, and labeled over 900 individuals, all of which are monitored with some frequency. To date, we've contributed over 760,000 observation records indicating the phenological status of these plants, up to twice a week. We're a pretty important partner for the National Phenology Network because collectively over the last 4 years, the CPP contributed observations have represent about 20% of the observations that were submitted from ground-based observers to the USA NPN National Database over the same time period. And so with these first 3 years of data, we're beginning to be able to detect associations between phenological onset dates and climatic attributes such as seasonal or monthly rainfall and monthly minimum or maximum temperatures. And I'm just going to have time to give you some examples of what we're finding. So the 7 pilot parks are shown here, extending from Redwood and Lassen Volcanic National Parks in the north. The Marin Headlands, Golden Gate National Park, and John Muir National Historic Site here. Sequoia and Kings Canyon as one of our other montane sites, the Santa Monica Mountains, and Joshua Tree. None of this would have been possible without the initiator of the project, Angie Evenden, who is the research coordinator of CESU at Berkeley, along with the contacts and local heroes at each of our local parks. But really the groundwork was done each year by seasonal interns, contractors, and volunteers who we trained and who we trained to train. Over the course of the last few years, for all the targeted species in my lab, we've created a number of tools to facilitate the monitoring by amateurs and professionals, and these include these species profiles for each of our 30 targeted taxa. We use on the ground the standardized protocols of the USANPN, which include these pretty simple, user-friendly data sheets, which just amount to the observer noting on a given date whether, yes or no, they see each of a given suite of phenological phases, which are specific to the life form represented by the taxon in question. Okay, so the general question that I have time to explore a little bit today is this. How do local conditions at a site where we're observing a set of individuals of one or more species, how do local conditions, such as monthly temperature or cumulative rainfall, during the period preceding leafing and flowering, affect the onset date, the day of the year from 1 to 365, of these phenophases? So the first example I'm going to show in a simplified form is the effect of May temperature on the onset of late summer flowering of coyote brush, Baccharis pilularis. And we've monitored Baccharis at a range of parks listed here from the north to the south, pretty much all along the coast. And the simplest question we might ask is just what is the relationship, the bivariate relationship, between the day of the year at which observers first started seeing flower buds or flowers versus the mean minimum temperature of the May preceding that observation. And so each site, each point on this graph, and all the graphs I'll show you later on, represent the mean flowering time and the mean maximum temperature of May at that site. And so we have 23 sites shown here for 2012, and you can see by this positive relationship that the sites where we had warmer May maximum temperatures, those exhibited later or delayed flowering. The R-squared value here, not too bad, 0.41. Okay, so this is just a bivariate relationship regression where the alpha value represents the slope of this line. Last time I checked, May is not the only month of the year, and so we decided to build some models with additional months, and we've done lots of these, and I'm just going to show you a couple of examples. So in these models, DOY, the day of the year of onset of a given phenophase, is still the dependent variable, but now we can include other independent variables in the model. So for example, in a model in which we include the first 3 variables as the minimum mean daily temperature for each of the preceding, for 3 months preceding our observed flowering season, we can look at the slope of, the slope relating January temperatures to DOI, February temperatures to DOI, March temperatures to DOI, and then we can do the same thing in the same model with precipitation. And so by building a multivariate model like this, we can ask, for example, what is the effect of warm Marches independently of what happens in January and February on the DOI of a given phenophase? And so now let's look again at Baccharis pilularis, but examine the independent effects of January, February, and March temperature and rainfall. Okay, and so now we've got 6 bivariate plots, each examined independently of the others, and I just want to point out a couple of things. First, this multivariate model didn't do too badly. It explains 32% of the variance, and I just want to point out a couple of things. First, not only the significance, but the direction of the slope differs among the independent variables. So for example, this is the effects of the preceding January's temperatures, minimum temperatures on the DOI of flowering and flowers or flower buds, and there's no significant relationship. In fact, of these 3 months, only March has a significant effect, and unlike the effect of May, we see a negative significant slope, meaning that sites where Marches were warm show earlier flowering than sites where March was cool. Similarly, the effects of the independent monthly rainfalls are also qualitatively different. Sites where the preceding February was wet had later flowering, whereas sites where the preceding March was wet had earlier flowering. In other words, the effect of minimum temperatures and cumulative rainfall depend on the month. Quercus lobata is another example that makes some slightly different points. And here we're going to look at the day of onset of leaf emergence and of flowers and flower buds. Our best data were from sites only in Southern California, and so this is what I'll show you now. First, with respect to breaking leaf buds, note the R-squared, 0.96, 96%. In other words, just with these 6 variables, we were able to explain 96% of the variance in the date of onset of breaking leaf buds. But the situation is no less complex. If we look at the independent effects of December and January and February, they show some opposing patterns. So for example, sites where December was warm showed earlier bud break, whereas sites where January and February were warm showed delayed bud break, as if we don't get significant cooling in January and February, plants won't get the cue that they need to really make that transition as soon as it warms up in March. Rainfall, on the other hand, had a significant delaying effect in all 3 months. So the effects of T-min depended on the month, while high rainfall significantly and consistently delayed leaf bud break. Slightly different story with respect to flowers or flower buds. The effects of both climatic variables during the preceding winter depend very clearly on which month we're looking at, and these slopes change over time, indicating that the effect of being warm depends on when you are warm. So typically, historically, many long-term attempts to link climatic conditions to phenological events have either taken annual means or winter means, which prevent you from detecting these annoying attributes. And then just the final example I wanted to give to rub it in is with California buckwheat, monitored throughout the south from the coast to Joshua Tree. And here we find a similar pattern as we did with Quercus lobata. The effects of both T-minimum, minimum temperature and rainfall depend on the month. With respect to temperature, warm temperatures in January accelerate or advance the appearance of flower and flower buds, while the same conditions in February delay them, and the effects of rainfall too change throughout the season. Again, here we have a pretty good, pretty high fit of the model, explaining almost 75% of the variation. What I've done here is just summarize the R-squares of different models, most of them, actually all of them, including 6 different monthly rainfall or temperature variables, to make a couple of points. First, the first 2 rows reflect the fit of the model to different phenophases, the phenophases of the different independent variables, depending, in coyote brush, depending on whether we're looking at the effects in January, February, March, or the summertime effects. Now, I was interested in this species in looking at both the effects of winter conditions and spring conditions, because this is a summer flowering species. And so I thought maybe the spring conditions would provide a better fit for the model. But with the exception of the onset of pollen release, the spring conditions actually did not explain as much of the variation in the onset date of these phenophases as did the winter conditions. So there appears to be a bit of a delay in those effects. In the second two species, Quercus lobata and Eriogonum fasciculatum, I just looked at winter conditions because they predictably start becoming phenologically active in the winter-spring transition. And I was really stunned, just to remind you, stunned by how well the models for Quercus lobata worked. And Eriogonum explained a fair amount of the variance as well, but I would point out what you can clearly note, which is that the winter conditions explained variation in some phenophases better than others. So flowering and fruiting onset dates were explained quite well by the model for California buckwheat, while the appearance of young leaves and open flowers was not. And I would emphasize something, a really important thing that we noted very early on in examining the phenophases in our Clarkia taxa, particularly those in the chaparral. And this is that they fall, as a model for phenological observation, they fall well outside the envelope of the model that's provided by the temperate zone species that the National Phenology Network's protocols are particularly well suited to allow. And the main issue in our Mediterranean climate is that our plants many of our phenophases are cyclical, appear cyclically and episodically in response to rainfall. Moreover, leaf out, for example, is not a phenomenon that emerges from well-protected bracts at a single time and synchronously throughout the rest of the season. So we did spend a lot of time kind of educating our good friends back in the National Phenology Office in Tucson to let them know that bud break is not even a phenomenon you can fruitfully talk about in species like Eriogonum fasciculatum, in Adenosma fasciculatum, in lots of taxa that don't produce even obvious buds. So what about some predictions that we might make? And this is a very slippery slope, and I am happy it's the end of my talk. So if we matched those slopes we saw in the previous slides to predictions of warmer, whoops, this is an old slide, sorry. I was supposed to have been replaced. Warmer winters and drier winters, we would find that warmer winters result in Baccharis early flowering, in Quercus later leaf out and later flowering, but ambiguous effects on buckwheat. Drier winters result in earlier leaf out and earlier flowering for Quercus and later flowering for Eriogonum. What I think this means is that, and this is really going out on a limb here, is that, oh, this is the slide I meant to have, is that changes in the timing of floral and vegetative resources at the community level are going to change in highly unpredictable ways. And we, at this point, have no idea what this is going to mean for pollinator communities, for herbivore communities, and for the plants that either benefit from matching those populations and communities or that benefit from missing those communities in the case of herbivores. And so just in summary, the effects of our temperatures differ among winter months as well as among phenophases and species. The effects of monthly rainfall on DOI are typically stronger and more consistent than T-min, but not necessarily so. Multivariate models can account for a really high proportion of the variance in spring phenology, but the associations between monthly conditions and the onset of DOI, or the DOI dates, differ among phenophases and species. And finally, under the right or wrong conditions, species-specific responses can lead to changes in the community-level distribution of floral and vegetative resources, which under some circumstances where some species flower earlier, some species flower later, we could see a thinning of floral resources, the consequences of which are entirely unknown, I think. And so I just want to remind you of those people who worked most closely with me to set up the phenological monitoring in our parks and natural reserves. And it's been a labor usually of love.